This video is part of a series exploring and documenting the development of a robot for artificial general intelligence experimentation. Mechanically, the robot is complete enough to support more interesting intelligent software development, which I'll cover in future videos. And this robot is controlled by brain simulator modules using spiking neurons. These will integrate easily into other AGI development, which is already in place. In a previous video, I explained why the development of artificial general intelligence will require robots, because the only way to understand the real world with real objects is to be able to interact with them. Any AGI needs to perceive its environment and take actions that affect the environment. So, what is the simplest robot which might manifest intelligence in the real world? This video describes the initial robot and the reasoning behind some of the design decisions. AGI will require significant computational power, and trying to load this onto a mobile robot isn't practical. So using powerful desktop computers to act as the brain while wirelessly controlling a robotic body is the way to go. We can think of signals going from the body to the brain as senses, analogous to sensory nerves, and signals going from the brain to the body as actions, which are analogous to motor nerves. Here's an outline of this robot's capabilities. If there's interest, I'll make a video with more details. Let me know in the comments if you're interested. The robot is built on a mobile platform so it can move about and explore its environment. The robot can manipulate objects in its environment with its arm. The arm includes 6 servos with a gripper positioned so the robot's camera can see it when needed. On this platform, the single camera is mounted on a pan-tilt mount so the robot can scan its environment. Robotic speech is not yet on board, but is part of the brain simulator functionality for future edition. For sight, the robot has a single camera. Here you can see the camera on its pan-tilt mount, and interestingly, the robot is looking at the internal workings of its own brain. The robot can sense its internal motion and positions of all of its joints. And the robot has the equivalent of an inner ear, with solid-state gyros and accelerometers which report changes in motion and direction. Hearing, like speech, is not yet on board, but is part of the brain simulator's functionality. Finally, there are a few tactile sensors at the gripper. Although software development is still in the early stages and Wi-Fi still has some issues, the mobile platform includes proportional motor control, so moving slowly is possible even under changing load conditions as shown. Notice that the platform keeps moving straight even when obstructed on just one side. This is not a high-precision or high-performance robot, but it's significantly less than $1,000. It seems like a good place to start. When you stop to think about it, the human body isn't all that precise either, although it improves with practice. And even with practice, without looking, you can only position your hand within a few centimeters of a desired position. Then you use visual or tactile feedback to get more precision. It takes an infant a year to learn to walk or grasp an object she sees, and we'll see if this robot can learn more quickly. We'll also see if the limitations of the robot impede its ability to comprehend and perform intelligent actions, and in what areas more capabilities are needed. An obvious question is, why not start with a better robot with improved senses in the first place? Well, remember, the objective is to work toward AGI as opposed to building the best possible robot. If, for example, I add LiDAR or ultrasound for 3D ranging, then the AGI's vision system development won't be as robust because it won't be necessary. Likewise, superior servos could be more accurate and repeatable, but might eliminate the need to develop abilities like eye-hand coordination, which represent a significant portion of the human brain's neurons. So, this minimalist approach I'm taking with the robot will place a greater emphasis on the brain, which will have to learn to compensate for the body's limitations. This has been the first introduction to the Brain Simulator's robotic counterpart. I hope you've enjoyed this video. You'll be able to try out these examples on your own by downloading the Brain Simulator, and the robotic code is written to support a wide variety of different robot configurations. You can also download the source code from GitHub and contribute to the project. For more on how this fits the overall strategy leading to artificial general intelligence, read my books, Will Computers Revolt and Brain Simulator 2. Links are in the description below. Also, please take this opportunity to like, comment, share, and subscribe. And as always, thanks for watching.